Welcome, my name is Mats Olshammar. I will first talk about four-stroke engines with Otto, Atkinson and Bodak cycles. Then I will talk about the free-piston linear generator, the Ilmor 5-stroke engine, and finally the Olshammar engine. This picture shows a one-cylinder four-stroke engine. Air comes in from the left, exhaust leaves on the right. There is one exhaust pulse, then an intake stroke, a compression stroke and a power stroke. It's problematic to fit a turbo to this engine, as the exhaust stroke driving the turbo is not in phase with the intake stroke. The uneven exhaust pulse also causes extra stress on the turbo. The Otto cycle has the same stroke volume for compression and expansion. It gives good power, but it's not very fuel efficient. The Atkinson cycle keeps the intake valve open a little longer, so that some air is pushed out again. The compressed volume will then be less than the volume expanded. This is more fuel efficient, but gives less power than the Otto cycle. The Bodak cycle closes the intake valve earlier, so there is less air to compress, and the result is similar to the Atkinson cycle. This is the free-piston linear generator. It's a compact design that could work as a range extender for electric cars. It works as a generator during the power stroke and as a motor during the compression stroke for a two-stroke design. For a four-stroke design, it will also work as an engine during intake and exhaust stroke. A four-stroke design can have smaller compression volume than expansion volume and therefore be fuel efficient. A two-stroke design is more powerful for the same size. Studies have shown that it's important with a low moving mass for efficiency. One problem is therefore to build a lightweight linear generator motor that is powerful. Another problem is to build an electronic controller that can efficiently switch between engine and generator mode, and also adapt to fast variations in the combustion dynamics. A piston connected to a normal crankshaft has a fixed top dead center and a fixed bottom dead center, but a free piston does not. Power electronics will control its top dead center and bottom dead center to give the correct compression and expansion ratio. Another difference is that valves are not controlled by a camshaft, but with new free valve controllers that are still under development. The dual cylinder version has two combustion chambers and can give higher power for a smaller size, but it is more difficult to control its piston motion. The opposed cylinder version has two pistons that share the same combustion cylinder. It's a well-balanced design, but it's also difficult to control. This is an inline two-cylinder four-stroke engine. First, there is an exhaust pulse from the left cylinder and then from the right cylinder. It's more suitable for a turbo than the one-cylinder engine, but the exhaust driving the turbo is still uneven. There is also vibrations as the two pistons move in tandem up and down. You therefore need counterbalances on the crankshaft. The torque is also uneven and you therefore need a heavy flywheel. This adds rotating mass and makes the engine less responsive. This is the Ilmor 5-stroke engine. It was invented by Gerhard Schmitz in the year 2000. The idea is to add an extra exhaust cylinder, but there is no combustion in this. This cylinder will first be powered by exhaust from the left combustion cylinder and then from the right. Ilmor Engineering has built a working prototype, but they haven't shown this to be more efficient than other engines. There is an advantage with the extra expansion volume that should give better fuel efficiency, but I believe that the extra valves and the extra large exhaust cylinder is negative to the efficiency. I also believe that this design is not good for the turbo, as you still have two exhaust peaks, but they are weaker and they have been moved 180 degrees forward. There are, however, advantages with this design. The extra piston counterbalances the other pistons, and the extra torque from this piston evens out the torque curve. This is the Olshammar engine. If we compare it with the Ilmor engine, we see that the exhaust cylinder is smaller and there are no extra valves. The idea with the Olshammar engine is that half of the exhaust shall flow directly to the turbo, while the other half is pushing down the exhaust piston. This way we can divide the two exhaust peaks from the combustion cylinder into 4 smaller exhaust peaks that will drive the turbo. We will therefore get the advantage of the Ilmor engine, but with a smaller exhaust piston and without the extra valves. We will also get better performance from the turbo. To the left in this picture are 3 combustion cylinders in line behind each other. They drive a crankshaft and it's connected to a second crankshaft in a 2:3 ratio. When the first crankshaft rotates 2 revolutions, the second crankshaft will rotate 3 revolutions. A single exhaust cylinder can then serve 3 combustion cylinders. If we look at the blue exhaust curve from the combustion cylinders and combine this with the yellow curve from the exhaust cylinder, we can see that this creates a very smooth gas flow to the turbo. This is an inline 6-cylinder engine. Cylinders 1 and 6 move up in tandem, cylinders 2 and 5 move down, and cylinders 3 and 4 are at top dead center. One would think that the exhaust from a 6-cylinder engine would be as smooth to the turbo as from the 3+1 cylinder engine I showed before, but that's not true. The exhaust from cylinder 6 has just started, and the pressure is much higher than the exhaust left in cylinder 3. Exhaust from cylinder 6 will therefore prevent cylinder 3 from breathing out properly if they are mixed. 6-cylinder engines are therefore designed with 2 turbos or 1 twin-scroll turbo that separate the pulses from different cylinders. This is a press picture from Mercedes before the 2014 Formula 1 season. It's a V6 engine with 3 cylinders on each side. And you can see 3 primary exhaust tubes merge into a common collector tube that's connected to 1 inlet in a twin-scroll turbo. The 3 primary exhaust tubes have the same length and are tuned to give resonance at a certain RPM, where they help the cylinders breathe out better. This second picture shows the actual engine used by Mercedes during the 2014 season. Here we can see a compact, log-style exhaust with thermal insulation. This gives higher pressure to the turbo at all RPMs, and this compensates the loss of efficiency gained at certain RPMs by using a tuned exhaust with long primary tubes. The idea with the Olshammar engine is to have a compact exhaust with an exhaust piston that will give resonance at all RPMs. This picture shows 3 combustion cylinders to the left. To the right is 1 exhaust cylinder with a free-piston linear generator that can also work as an engine. This allows us to smooth out the exhaust pulses before they are sent to the turbo. But it also allows us to shift phase of the exhaust piston. The pulses are then amplified, and this gives sharper and more powerful pulses to the turbo. This is not fuel efficient, but it helps the turbo to spool up faster and can be used during acceleration. When there's no longer need for extra power, we can smooth out the pulses again, and the linear generator will give us electricity to store. Powerful pulses are useful when the exhaust flow is lower than the design limit for the turbo, but smooth flow is better when you get close to the limit. This design will therefore help the turbo from low flow to high flow. The advantage with the free-piston design is that we can change the angle between the cylinders to help the exhaust flow easy from the combustion cylinder to the turbo. This second picture shows a free-piston linear generator also being used for a combustion cylinder. This could be a future design, but for the moment it's much easier to only use a free piston for the exhaust cylinder. There's less force on the exhaust piston, so the piston and the moving part of the linear generator can have a low moving mass, which is efficient. The exhaust piston will also generate electricity every second stroke, which is better than the 4-stroke combustion cylinder that will only generate electricity during 1 out of 4 strokes. There is also less demand on the electronic controller, as the control of the exhaust piston is not critical to the combustion process. And finally, there is no need for new free valve controllers, as there are no valves on this exhaust cylinder. I therefore believe that it will be relatively easy to build the 3+1 design shown in my previous slide. One could also use 2 smaller opposing pistons to get less vibrations. This picture shows an extra exhaust port number 19 and an extra exhaust channel number 28 that can lead exhaust to the right inlet of a twin-scroll turbo. This is only done when the piston is close to bottom dead center and valve 23 is open. There's also a second exhaust channel, number 17, that's always open. When the engine is idling, then we reduce the back pressure by parking the piston at bottom dead center, and we open all valves, number 20, 21, 22 and 23. When there's some load on the engine and only a small volume of exhaust, then we close all valves. All exhaust is then routed through channel 17 to the left inlet of the twin-scroll turbo. When there's a little more exhaust, then we open valve 23 to let exhaust pulses reach both inlets of the turbo. When there's even more exhaust, then we open up valves 21 and 22 to even out the exhaust pulses between left and right inlet, so that the turbo can handle as much exhaust as possible. When there's too much exhaust, then we also open valve 20, the turbo bypass valve. The advantage with this design is that it offers good performance for all RPMs, and it is very responsive, as we can use the linear motor to push in extra energy in the pulses and then spool up the turbo fast. It's also possible to have 4 combustion cylinders to the left side, particularly if it's a diesel engine with low RPMs. I would call this a 4+1 combination. It's also possible to have other combinations, and this new picture shows a boxer engine with 6 combustion cylinders and 2 exhaust cylinders in a free piston dual cylinder design. I hope you have enjoyed this presentation, and thank you for your time. If you'd like to know more, then contact me on this email address, mats@olshammar.se.